Please welcome Dr. Mike Pook.
Thank you very much, Eric. It's a great honour to be here today and, in fact, to learn that somebody remembers me since I've been out to pasture for quite a long time. Today I'd like to talk to you about climate variability. That's the term I'm using quite advisedly. I'm not talking about long-term change or anything of that sort. I'm just reminding us that what we experience in Tasmania is a very, very variable climate. And I'd like to consider some of the reasons why we do have that situation here. If I can start with, is this all right for me just to push this button, is it? All right. So by way of introduction, I'd just like to talk about a few points. Firstly, what do we mean by the term climate? There's in fact quite a lot of confusion about that term and how it relates to weather, how the two can be differentiated. So what then characterises climate variability is the next question, and I'll mention a few points about climate variability versus climate change. Now this is the one I might have problems with. I'll let this just run for a moment and then I'm going to run it through again. But what we're looking at here is 1 month of satellite imagery from the Japanese geostationary satellite, or one of their satellites, back in August 2003. Those satellites are located over the equator at an altitude of 36,000 kilometres, which gives them a view of the tropics and subtropics down into the higher latitudes, but not obviously to the poles. Now, with an infrared image, what we're looking at is the radiation that's being emitted from the Earth right up through the atmosphere to the satellite. And we're very fortunate, of course, that that radiation can get through into space. In quite a few areas of the spectrum, the radiation is trapped by a number of gases, particularly water vapour and also carbon dioxide. But at around 10 micrometres, most of that radiation gets through to space. So not only does the satellite see it, but that radiation is cooling the Earth. It's moving right through the atmosphere out into deep space, and it's returning radiation to space after it's received it from the sun at the Earth's surface, and we'll look at that in a minute. But what I wanted to show with this is that, if I can get it to run again, the dark and black indicates the warmer temperatures, the higher temperatures, and the very white represents cold. So initially we're seeing systems moving across, where are we? Somewhere here. We're seeing systems moving from west to east, but then in this part of the process, systems have now moved northwards, and we're seeing much more north-south or meridional flow. Then back to more westerly flow. You can see the jet stream across central Australia. That's the very white cloud, wispy-looking cloud with the subtropical jet. And then more frontal systems moving in, shearing off over Western Australia there. And you just notice the cyclonic circulation in those systems, and then they join the flow again as they move southwards. So this is weather in action. This is what we see day to day, producing the wind, producing the temperatures, the cloudiness and the rain. But if I were to summarise what happened in that month, you might be surprised to see that with all that action, with all those clouds, then there isn't an enormous amount of rain being received. And here we've broken it up into Hobart, here and Launceston in red. And you can see early on a couple of decent falls of rain, around 10 millimetres or so. But it's not until we get right up towards the end of the month that we see a major rain event in Launceston, with Hobart recording a similar one, but then another day of rain after that. So that actually summarises the rainfall for that month by recording each day's return. Now you could, if you like, look at the individual charts associated with those events, and that would tell you something about the type of flow that we have. But I understand that many people don't immediately understand how to read a chart, so what I'll do is I'll just put up an old chart here, earlier on in that same year, and let's just imagine how the winds flow in a situation where we have, say, high pressure down in here, and we've got low pressures up in the top and down in this region. So you'd expect immediately that the air would blow from high to low pressure. But when it does that, or when it tries to do that, you've got to remember that we're on a rotating body, an accelerating body, and we don't see the air moving directly from high to low pressure. In fact, what we see is the air settling down to blow parallel to the isobars, with the lowest pressure on the right. So that's the old Byers-Ballott's law, transformed from the northern hemisphere to the southern hemisphere. So over here, you've basically got this southeasterly flow. Down here, we've got a northwesterly, a westerly in the south. And then you notice that we also have these breaks in the flow, fronts, for example, and troughs, and they're very much associated with day-to-day weather. So going back to those charts, this might help a little bit now. You can see that in the early part of the sequence, we had strong westerly winds blowing through this region, with fronts crossing Tasmania. A little later on, we have southwesterly change, and then this area here, this is towards that big rain event. We've got two cut-off lows over the mainland moving south. We've got a blocking high-pressure system to the southeast, sort of situation that we've been seeing a lot of lately. And right at the end, northwest flow, which is favourable for rain in this part of the world. But any meteorologist will tell you it's all very well looking at surface charts, but you really need to know what's happening in the upper atmosphere. And here I've reproduced the same chart for at least for the 24th of August, but in this case we've got mean sea level pressure here, and then we've got the temperature anomaly through 6 kilometres or so of the atmosphere, the blue showing that it's very cold north of Adelaide, and quite warm over Victoria and Tasmania. This is the rainfall for 24 hours, showing it extends right from Queensland down into Tasmania. Another similar situation to what we're experiencing now. And then in the upper air, we can actually draw a chart. Looks like a surface chart. We actually draw them as contour lines, but there you have a closed low pressure system in the upper air, and out in this region you've got the jet stream at about 10 kilometres. So strong winds flowing across Australia and then affected by that low pressure area north of Adelaide. And now if we wanted to go back in time and see what the weather was like during 2003, excuse me, we could produce a chart like this, a diagram like this, a bar chart, which shows the actual rainfall against the mean rainfall for each of those months. And what you see here is the month that we're talking about was actually quite a high rainfall month for Hobart, something like 105 millimetres, twice the average. But then look at the rest of the year. The first part of the year, very dry. Then a burst of rain in March. Average rainfall then until we get to August and September, and then virtually nothing during November. This is a very, very good example of what we see from year to year and day to day, and it's the sort of climate variability that we live with, not just because we're in Tasmania, but partly because of that. But this is the difference between looking at weather and looking at climate. You can't tell me anything about the systems that produce that rainfall, and yet we showed earlier on that we can show the satellite imagery, we can show the charts, we can show the individual rainfall, and we could even show rainfall for shorter periods than one day. But when we look back in time, this is what we get, and this is really looking at climate. And when we look even on a longer time scale, say for annual rain, we see the familiar pattern for Tasmania of the extreme rainfall on the west coast, over 2,000 millimetres, and up around Mount Reid and Lake Margaret, sometimes over 4 metres of rainfall there, but the average about 3.5, falling away quickly to the Midlands, where generally less than 500, and then another peak in the Northeast Highlands. But then I thought, well, let's just investigate what the maximum rainfall in any part of the state is during the entire year. So here we think we've got the highest rainfall. So does that contain the highest daily rainfall? Well, actually, no. If we look at these places, Mathina, Grey and St Mary's, we actually find that the highest daily rainfall ever recorded has been recorded here. That might have changed with this recent event onto the Great Western Tiers, but so far I haven't seen that published. So the situation for Tasmania then is that we've got this variability in rainfall particularly, but also in temperature across the state, largely caused by topography, but also because of our placement in the westerly wind belt. So the highest rainfall occurs in this region here to the west of the highest topography. And then we have that secondary point up in this region. But you can also see that places like Grey, Elephant Pass and so on are very, very high locations, and air from the east is going to seriously influence them. And the highest daily rainfall totals then actually were recorded in 1974, in 1929, would you believe? And I'm sure many of you have read about and heard about the 1929 flood, which actually Dr. Tony Large wrote a book about Ulverston back in 2004, I think it was, where he talked extensively about the flood and the loss of life. There were something like 22 people killed in that flood. The other location is down at St Mary's, and that was in the 2011 flood. So let's just consider what cloud and rain generation processes we observe in this part of the world. Well, obviously, the first one which would come to mind would be orographic uplift. So in a strong stream, if you force air to rise and it's moist enough, it will produce cloud. Hence, we get a lot of rain on the west coast in the westerlies. Cold and warm fronts are significant producers of rain in this part of the world and also down south in Hobart and the southeast. But one of the most important ones is this slow, widespread ascent in cyclonic systems, such as we saw with that rainfall on the 24th and 25th of August 2003 in the slide I showed previously. Those small cut-off low-pressure systems are associated with this sort of ascent. And finally, convection, which results when you have instability released in the atmosphere by heating from below and cooling aloft. So if you have a pool of cold air over the top, then it tends to enhance convective activity. So going back to that flooding in April 1929, I'd just like to remind you how much rain fell at Mathina. We saw that Mathina had the second highest daily rainfall of 337 millimetres there, but note that it had already received 132 millimetres on the previous day, a total getting up towards 500 millimetres in 2 days. So it's not surprising that that was an extraordinary event. Tony Large went to the Bureau and he copied some of their old charts. So this is the chart, only a surface chart, but it shows in a messy sort of way that we had this low pressure system near us, which looks a lot like some of these low pressure systems that, that I drew your attention to in the previous satellite imagery. So these are some of the images from that event. This one is the 1929 event. But just to remind you that these lows don't only produce rainfall, but also violent winds and terrific seas. This is that tragic 1998 Sydney-Hobart yacht race event when so many sailors lost their lives. This is the event in Hobart in 1960 and the southeast. So this one was very much in the north and northeast. This one was more in the east and southeast. But similar systems, meteorologically speaking, and just putting them side by side, you can see there that we have the 1929 one over here, and this one is, actually I can't see that one, that's 1998, this one up here, and this one is 1960. But notice those low pressure systems in each case, the little areas of yellow, and even possibly more importantly, notice the red area, which is high pressure, and in this case extending right to the south of the low. This is a blocking high pressure system which actually stops that system, the low, moving quickly away and enhances the rainfall. And this is one of the characteristics of weather in the Tasmanian region. We expect systems to move through quickly from west to east, but quite often, particularly in winter and spring, we get this delayed effect caused by blocking high pressure systems. So there's two examples. Now, why do you think these are so important? Well, if you look at the cloud that produced the rain and then track back over time where the water came, where the air came from, or the parcel containing moisture came from, you find a very interesting feature of this sort of flow in the Australian region and Southeast Australia in particular. This, the wrong thing, this area here is the cloud base that we're going back, we're tracing ray paths back from. We take them back right down to the surface, and you notice that the colour near the surface changes and becomes blue, almost purple in many cases. And that's to indicate that that's the moistest air. And that air then moves into the low pressure area and is carried to high levels fairly quickly. And it's in that process that it releases its water, condenses out and produces cloud and ultimately rain. But the situation off northeastern Tasmania is perfect for this because those systems can access the warm waters from the remains of the East Australia Current and the Tasman Sea in general. So I've shown you those individual cut-off systems, but some years ago, colleagues and I in Hobart produced an analysis of the systems that produce the rain during the growing season for grains right across southern Australia. And we included Tasmania in that, particularly the Fingal Valley and the East Coast. And what we did was to try to separate out the main systems into their component types. And this analysis, which we published in 2012, shows that the rain associated with those cut-off low systems, and often blocking as well, is very, very highly associated with the east and the northeast. More than 50% of the rain in those areas is produced by those systems, and then you see it falling away on the west coast to a much, much lower value. But then if we look at frontal systems, which is actually an important source of rain for Launceston area and the northern Midlands, then you see that the frontal systems are particularly important in this area, whereas on the east coast they're less important. So this is essentially climatology of those systems, and I hope that you can see how we're moving from weather to climate and climatology as we go. And in this way, I'd just mention that a summary of what weather is, or what it means, is that it's effectively a short time scale. It's what you're in, it's what you're experiencing. A very famous scientist, Dr. Lineker in the United States, famous for all sorts of chaos theory, etc., once said that climate is what you expect and weather is what you get. And so climate is not showing you individual systems at all. As we've just seen, it's a larger timescale, a longer timescale, and it could be months to centuries and even millennia. It's averaged over many weather systems, not just one, many systems with individual features not predictable, and we know that the average might be predictable because we could use statistical methods or now computer models, but effectively forecasting climate is not easy. It seems to me that for many people it gets easier the farther away you look, but if you've been a weather forecaster, you know that it's a tough gig, as the young people say today, because you're never going to be completely right. There's always some element that's going to be slightly out, and no two weather systems are ever the same exactly. So then climate variability versus climate change. Well, natural climate variability occurs on all timescales. It's seasonal, it's interannual, it's decadal, etc. And very often it shows up in SST patterns around the oceans. But climate drift occurs as well, and we've all heard about some of these periods of climate, not getting into the ice ages, which we'll talk about next, but periods of time, the Little Ice Age, 1600, 1900, something like that. The climate optimum, about 9,000 years ago. The medieval warm period, when the Vikings sailed across the North Seas around 1,000 years ago. But secular climate change is another thing. That's where we move to a new climate state, such as the ice ages, the last one of which we emerged from about 15,000 years ago, and then we move into the interglacials, and we're currently in an interglacial, and we're in the Holocene period of that interglacial. But I'm not sure if you're all aware that when we were coming out of the Ice Age, or when the Earth was coming out, it very suddenly went back into the Younger Dryas, which extended from 12,900 to about 11,700 years. It was characterised by the Dryas flower, I think the Octopetala or something, I think it was called, those white flowers that had 8 petals, which is most unusual. They show up in the climatological record, the paleo record. But there are also, there are also some changes that have been produced by humans already, obviously. The urban heat island effect is very real, and it's pretty unlikely that many of the huge cities of the world will ever go back to the state they were once in. We've also got the effect of warming from the effects of greenhouse gases, mainly carbon dioxide, water vapour, which we're not putting into the air directly, and also methane. So let's look then at the climate system. How does it work? I think it's pretty obvious that all the energy has to come from the sun. It's a tiny amount of the energy the sun produces, but we pick up what we can, and that's the primary input for the energy driving our climate system. The other part of the system, though, is the atmosphere. And we need to look at at what makes up the composition of the atmosphere and how the heat is radiated through and out to space, and how heat is transferred from where it's received, generally in the equatorial regions, to the high latitude parts. So the Earth also plays a part in this because it reflects and absorbs and stores heat. It also produces dust from the lithosphere with strong winds, and that dust makes up cloud condensation nuclei, which is an important part of the radiation transfer system, because clouds have an effect generally of cooling the Earth, but not always. And then volcanism is important. The Earth's contribution via volcanism. I'm sure you've all heard of Krakatoa in 1883, but the Mount Tambora in 1815 was a more significant volcanic explosion. And in fact, in Europe, in the following year, in 1816, that was actually dubbed the year without a summer. Temperature fell by about 0.6 of a degree worldwide because of that event, probably 0.5 with Krakatoa, and Mount Pinatubo, was that in 1991, I think. That is thought to have reduced the temperature by about 0.5 as well. And then we have to look at the ocean, because the ocean, in fact, stores much more heat than the atmosphere, and the ocean also has very slow-moving tides and currents. These are internal currents which move heat around and then release it to the atmosphere. And lastly, we always have to consider the cryosphere, which is that area covered by snow and ice, mainly at the polar regions, but also in the mountainous regions, because that affects the reflectivity, what we call the albedo, of the Earth's surface overall. So I'm going to look at the role of the sun and orbital cycles, the influence of the ocean, something about annual and seasonal cycles, and the main climate drivers that affect Tasmania. And then climate trends and change we're not going into in any great detail, but obviously any climate trend has to be considered on top or in the background of any variability. And here's a diagram showing the Earth in its orbit around the sun. I'm sure most of you have seen this, and going back to school days, this is quite a nice diagram because it raises quite a few issues. Firstly, if we just look here, you'll notice that the Earth, around about the summer solstice, the Earth is closer to the sun in the southern hemisphere than it is to the northern hemisphere during its summer. So at perihelion, which is not quite at solstice, it's actually around January the 4th each year, the Earth receives, and that means mainly the Southern Hemisphere, receives 7% more solar insolation than the Northern Hemisphere receives when it's in its solstice. The other thing to note is that the Earth is tilted on its axis to the perpendicular, or the normal to the plane of the ecliptic, at the moment by about 23.5 degrees. It's also wobbling a little on its axis as it precesses. And those two effects, that change in the angle of tilt, occurs over about a 40,000 year cycle, and the precession occurs over something like 23,000. Those combined effects are thought to lead to ice ages as they change and reduce the amount of insolation received, particularly in the Northern Hemisphere. The other thing to note is that this orbit is elliptical, it's not exactly circular, and it changes shape over a period of 100,000 years, and there's another cycle on there of about 400,000 years, which I know nothing about, but they talk about it anyway. But these three cycles are referred to as the Milankovitch cycles, and they're responsible for our plunging into ice ages and the return from them over many, many thousands of years. We need to consider the composition of the atmosphere because we want to know how it treats that radiation coming from the sun. And as we know, most of it is made up of nitrogen and oxygen, and both of those gases allow the radiation from the sun, which is centred in the visible and near infrared, to largely pass through the atmosphere rather. Clouds, of course, will tend to reflect it back, but about 47% gets through and heats the surface. But what matters next, of course, is that we have these variable gases. Water vapour makes up a variable amount up to about 4%. Carbon dioxide, now this is interesting because this table was made back in 1995, in fact, and you see the value of carbon dioxide there, and you can change that then to parts per million. That's how it's generally represented. But you'll notice I've put in the latest from Cape Grim there, and that gives you something like 400 parts per million now. Quite an increase over the last 30 years. And methane is normally shown in parts per billion. That one is variable but tending to increase. Now, the role of those gases is that in certain parts of the spectrum they actually absorb radiation from the Earth's surface and then they retransmit it back to the Earth, thereby keeping a blanket on our temperature. Now, you know, we constantly say, oh, well, we're worried about carbon dioxide increasing, of course, but it's worth mentioning that without carbon dioxide and water vapour in our atmosphere, our temperature at Earth's surface would be about 40 degrees colder than it currently is. So these are important sources of heat and trapping heat in the atmosphere. And interestingly too, when I was talking to one of my colleagues the other day, James Risby, he pointed out that volcanism is important, and certainly before we started putting fossil fuel emissions into the atmosphere, the Earth would actually drop in carbon dioxide quite a lot until volcanism actually replaced a lot of carbon dioxide as it occurred. The atmosphere is actually quite shallow as far as its working part. Down here, the troposphere, it's only about 10 or 15 kilometres thick. But the interesting feature is that the heat coming in heats the surface of the Earth, and then the temperature decreases rapidly with height, from about 15 degrees at the surface to something like minus 60 degrees at the tropopause. Then it heats up a little bit again because of the incoming ultraviolet radiation heating up these low-density gases in the stratosphere. But basically, the temperature falls with height quite steadily. And also the density drops off very rapidly, and the pressure falls to about half its surface value by the time you get to 6 kilometres. And poor old Icarus there, when he was trying to escape from the labyrinth, he was supposed to have flown too close to the sun and the wax melted, but I think really if he could have shielded himself from the sun, he wouldn't have had any trouble up here. He probably would have died from hypoxia rather than from falling into the water and drowning, as he's supposed to have done. And why is the ocean so important? Well, the atmosphere gets its driving force from the sea surface temperature because 70% or so of the Earth's surface is actually ocean. So it's constantly receiving an input from the surface, from the ocean. It provides moisture, it affects the air temperature, clouds, and therefore sunlight, and all of those aspects build up to produce pressure patterns, which then give us our wind speed and direction, and weather systems producing rainfall. It has a very long memory compared to the atmosphere. A wave in the ocean, say moving across the tropics, might take several months to travel from West Pacific to the Eastern Pacific, but off the equator, the waves returning across the Pacific Ocean, for example, the Rossby waves, may take 3 to 4 years, and they're carrying information with them each way. What else we can say is the heat capacity in the top 3 metres of the ocean is as much as the entire 10 kilometres of the atmosphere. And just looking at a typical picture of sea surface temperature, what you find is that most of the heat, of course, is stored in the tropical regions, and there's a constant attempt to move heat from here down to the high latitudes, which happens a little bit more easily in the northern hemisphere because the continents extend right up to the Arctic. But in the southern hemisphere, 60 million years ago, we saw the separation of Antarctica from South America and Drake Passage. So now we have a circumpolar current, and it's largely driven by bottom topography, so that it extends right up through this region. It goes north around the Kerguelen Plateau, and then it dips south around the Macquarie Rise. In this region, Macquarie Rise and Campbell Plateau, and then flows through Drake Passage. So it's more difficult for the ocean to move the heat southwards in the southern hemisphere, but it is being done by the atmosphere and the ocean. And we also have this very interesting phenomenon in the southern hemisphere, the extent of sea ice around Antarctica. It reaches its peak extent around about September, October each year, so it's just past it now, but that effectively doubles the size of Antarctica in continental terms. And then in summer, you see it disappearing quite remarkably, and then it comes back again very quickly in autumn. And if you've travelled to South America or South Africa by air, you will have seen, I'm sure, when the aeroplane takes the Great Circle route, dips down into the Southern Ocean. If you travel at this time of year, you'll actually see some of that. You'll see that sea ice extending out off the coast to about 60 degrees south. I remember seeing it on the way to South Africa and being very excited, telling my son and daughter-in-law to have a look as well, and they opened their slides, and there was a sharp intake of breath from all the other passengers because they were watching movies, many of were probably movie world, water world or something like that, which was the CGI representation of what was happening naturally. And I think it was a bit sad to see that nobody seemed terribly interested. So let's just get a rough idea then about how we settle down to get the wind directions. I showed you that if we have high pressure, and here it's across the subtropical ridge is across, around 30 south. On average, during the year, we'll have high pressure here and low pressure to the north and much lower pressure to the south, giving us our westerly wind flow across Tasmania, the so-called roaring 40s or furious 50s or screaming 60s or whatever you want to call them. But the roaring 40s is the general name we give to them. But I've said to a number of people on many occasions that the roaring 40s sometimes purr, and that's because we get these blocking systems forming. So looking at the seasonal cycle, I think we'll just do that first. And I'd like to look first of all at the top right diagram, which is winter. And you can see there that these dark spots, the dark reds and browns, are showing high pressure across Australia. That's the subtropical ridge, which moves right up over Australia during the winter months. This area of low pressure, the circumpolar trough, reaches peak intensity from winter to spring. And so we have this basic westerly flow. But just notice that it's not perfectly west to east. It's got these bumps in it. This is a trough and this is a ridge, and these are highly significant for the weather in Tasmania. In the summer months, the highs can't form over the mainland. They form away to the southwest in the Great Australian Bight and out in the Tasman Sea. So we have more easterly flow coming down and northerlies coming down, and the westerlies move away to the south. And then we have the intermediate seasons when the systems are moving backwards and forwards with the sun. But as I said before, meteorologists don't just look at the surface, because a lot of what's happening to your weather is being decided high up in the middle levels of the atmosphere and near the tropopause. In winter, in fact, we find that around about 10 kilometres or so in the atmosphere, we find that a very strong westerly jet forms due to the temperature gradients across the continent. That's the subtropical jet stream, west to east. The jet stream across the Indian Ocean tends to split into a part going down here and that part going across Australia. And in this area, near Tasmania, there's a bit of a backwater, excuse me, and that's where we see some of these high pressure systems forming, the blocking patterns forming, which is a key feature. In summer, quite different. The subtropical jet is not across mainland Australia at all. So the key influences on climate variability are this atmospheric long wave pattern, the pattern that I just showed you of those troughs and ridges in the westerlies, with blocking a major feature. The seasonal cycle changes things considerably, and then we start to get on to some of the remote effects, such as the El Niño Southern Oscillation and the Southern Annular Mode, which is the change in the westerlies, and the Indian Ocean Dipole. I won't go into the Madden-Julian Oscillation much today, but that's a tropical system which moves from west to east across the tropics over 40 to 60 days. And sea ice extent we've just looked at briefly. Back in 2008 or 2009, I think, we put this diagram together for a publication, and we tried to show, probably too much, but we showed what are the main effects on rainfall, particularly in southeastern and southwestern Australia and in Tasmania, because we were interested in the wheat areas here, and also just some of the grain and cropping in Tasmania as well. And you see this brown line here, that's meant to represent that trough ridge system. Now, a lot of the time, systems develop in this trough near Western Australia. The cold fronts move through, giving Western Australia its maximum rainfall during the winter months. Some of those systems then move through, crossing Tasmania, but sometimes if blocking occurs out in this region, the approaching fronts break up and part moves north and part moves to the southeast. And we can have periods of quite dry weather in Tasmania as a result of that pattern. Rainfall might occur in the northeast, but very little in the west, certainly well below average. So this is just a daily circumpolar plot of the flow at 6 kilometres above the Earth's surface, and there you have the trough ridge system, which is very common, and you can see how actually very active systems here move into a ridge system near Tasmania on occasions. So even during the entire year, that pattern persists to some extent. But if you were to look on a day-to-day basis around the Southern Hemisphere, this is a different way of looking from a satellite. This is a polar orbiting satellite picture. And as I said earlier, the geostationary satellite can only look in the scene below it from the equator. In order to look at the poles, you have to have satellites that fly in orbits from north to south across the pole. And they have a return period of about 100 minutes. They fly at 700 to 800 kilometres altitude, and they are able to take a picture of that region south of about 50, 60 south. And here, Tasmania is right up in this top area there. You notice all these frontal systems and lows encircling Antarctica, and they are responsible for producing the strong westerly winds. So if I drew a chart, this is even a chart in summer, what stands out is the number of low pressure systems, intense lows, huge low pressure systems, which encircle Antarctica. To the north of those, we have the strong westerly flow, and at the Antarctic coastline, we actually have strong easterly flow. The home of the blizzard, if you've read anything from Mawson, those winds are all blowing out from Antarctica, out across the coast from southeast. Now, the variation in the westerlies is sometimes referred to these days as the southern annular mode, a variation from when you have strong high pressure aloft. This is actually at 10,000, I've got to be careful, 3,000 metres. And this is low pressure, this is high pressure, producing strong westerlies. When the westerlies are strongest and closest to Antarctica, that's called the positive phase of the southern annular mode. And the negative phase is when the westerlies move up across the mid-latitudes, including Tasmania. And here I've just thrown in a working chart from 1965 to show just how strong those winds can get. This is September 1965, and it was the day on which Hobart recorded its maximum ever gust of 150 kilometres per hour. It's probably a little misleading because the isobars here are drawn at 2 hectopascal spacing, which is what we normally did with a working chart, but the charts that are displayed on television and in the press are at 4 hectopascal spacing, so wouldn't look quite as exciting as that, but nevertheless, it was pretty windy. And of course, if you get a change in direction with those strong westerly winds, you get the sort of event we had in 24th and 25th of July 1986. There were people skiing along the southern outlet in Hobart to get to work in Antarctic Division. And now I just wanted to show the effects on our climate of patterns such as blocking, which go on for a significant amount of time. I think many of you will remember the 1989 year when we had a lot of blocking activity. The rainfall over the southwest was extremely low. Now, to explain the diagram, the past rainfall, in this case annual rainfall, has been broken up into 10 percentiles. So you see here, average, it's actually the median, is the white area. And then as you go into the blue, you're getting into higher and higher decile numbers. The 10th decile is this very blue, and decile 1 is down here, very red. So on this occasion, the southwest catchments and western catchments of the hydro received very, very low rainfall relative to what they normally receive during 1989, but blocking produced enough easterly flow through here, the northeasterlies and easterlies, to give above average rainfall over the northeast and over the Furneaux group and even into King Island. So that's an example of blocking being a major influence on our climate variability. And then we can talk about El Niño Southern Oscillation as a remote influence. The normal situation in the Pacific is we have what's called the Walker circulation from the cold waters near Ecuador and Peru. We have the trade winds moving over to what's called the maritime continent north of Australia, which is warm, air rising and then returning via the Walker circulation, which is named for Sir Gilbert Walker, one of the famous meteorologists of the Indian service back in the 1920s. Now, when warm water moves into the central and eastern Pacific, or abnormally warm water, as here, we have the so-called El Niño effect, and it changes the Walker circulation so that it actually splits, and we have descending air to a large extent over northern Australia, producing drier conditions. The El Niño is named El Niño, the Christ child, in fact, because it was a warm current that flowed down the coast of Ecuador during December, and it was also associated with the year of abundance. But we now talk about the opposite of that. We talk about a situation where this situation actually amplifies, and the water is much colder in the eastern and central Pacific, warmer in this region, and we call that La Niña. That's the situation we have at the moment, and in that type of situation we have quite strong uplift, a Walker circulation that's even stronger and tends to descend more into the Pacific. So the El Niño is a situation where the warm ocean current flows down the coast of Ecuador and Peru. The Southern Oscillation is the seesaw in the atmospheric pressure and rainfall, and it's measured by what's called the Southern Oscillation Index. It's believed that ENSO is a coupled ocean atmosphere mode, and it recurs something like every 4 to 7 years. It's a tropical phenomenon. It's the very, very biggest climate signal on the planet, but it's, I suppose, I hate to say it, but every ENSO is different because You constantly hear whenever ENSO is predicted or whenever La Nina is predicted, the media just run with it and say, well, it means it's going to be a drought or there's going to be a flood. Sometimes, yes. It just moves the odds. Having ENSO in these particular states moves the odds, but it doesn't definitely ensure that you'll get some particular effect. So here's an example of the ENSO year 1982, one of the worst droughts in Tasmania's history. But notice in the southwest that the rainfall was about average. And this indicates something about El Nino, that the westerly winds south of Australia often strengthen during an El Nino event. And because of that, you get enough onshore flow and moisture deposition to maintain rainfall in the southwest. The 1997 El Nino was a much more intense El Nino than 1982. It produced dry conditions, but not quite as bad as 1982-83. And this shows you that every El Nino is different. The Indian Ocean Dipole, I'm getting towards the end now, is just to show you that this is an Indian Ocean situation. The positive phase is when cold water forms off Java in the upwelling there, warmer water to the west. That's the positive phase, tends to favour lower rainfall over Australia and even into Tasmania. And this is the current situation, the negative IOD. And when you combine the negative IOD with the La Nina, which is this situation down here, my colleague again at CSIRO, Gary Myers, produced this paper back in 2006. This shows you historically that the highest rainfall occurs when you have a combination of La Nina and IOD negative. You don't get much of the other sort, but here IOD positive and El Nino produces the biggest drought effect. But we showed in this paper, was led by James Risby, that in all areas of Australia, that the influence of those individual climate drivers differs with season and location. So that in summer, you can see there's the effect of blocking in Tasmania. There's some effect here of ENSO. And the southern annular mode, the strong westerly winds, appears to mainly just affect the far southwest of Tasmania, with little effect in the rest. So basically, what I'm trying to say here is that the day-to-day weather reflects the constantly changing pattern of atmospheric behaviour at Tasmania's latitude. So much of what we experience is contained within the weather, within the probabilistic weather, if you like. Climate represents the average of many of these weather systems, but it itself becomes variable on a range of timescales when you put all these together, when you integrate all these effects. The main influence on our weather is the hemispheric long wave pattern, bringing those troughs and ridges through, but blocking is an important part of that. And probably the main remote driver is ENSO, but when it is associated with IOD, it's more important. The southern annular mode is mainly directed at the southwest of Tasmania. And the correlation between individual climate drivers and rainfall in each region varies with the season. So I acknowledge, and I've put some references there to some of those diagrams that I've made. Thank you very much.
Thank you. Wanting to answer some questions.
Yes.
He was enthusiastic already.
Okay, as long as they're not too difficult. Is that politically, geographically, or? Yes. Yeah. Well, it's an active area of investigation. There was a project called Climate Futures, in which they did a lot of modelling of what's likely to happen. Generally speaking, because Tasmania is in this oceanic environment very largely, it was not expected that changes would occur very quickly or significantly, but in one of the realisations they did have increasing temperatures off the northeast, in the ocean water off the northeast, which would favour more rainfall from those cut-off low systems. But overall, essentially, that variability is such a big signal that it probably swamps any trend at the moment, but this is not to say it won't change in the future.
Is it true you believe Tasmania is the best state to see rainbows?
It's one of the better places to see because of the latitude. You know, you need to have your back to the sun, but you also need to have the angle of elevation of the sun low enough so that you get this reflection and refraction within the droplets. If you go to somewhere like Darwin, you won't see many rainbows, that's for sure, except very early in the morning or in the evening. So it is a good place from that point of view, but also because we get quite a lot of showery precipitation, which as it moves away from you allows the sun to shine through in the right sort of angle. Yes. He looks quite dangerous with that thing.
And two questions. Do you expect that the west coast of Tasmania will have really dry periods again? In terms, and I think this, thinking about this in terms of bushfires occurring on the west coast, because if we get really dry periods, the likelihood of bushfires is going to be much greater. That's one question. The other one is, when will we know whether global warming has played a part in these floods that we've got now in Tasmania? When and where will we find out that relationship?
Okay, I'll look first of all at the West Coast situation. Yes, it's almost certain there will be dry periods there, but the problem with the West Coast is that it's a very, very wet location, and you get these, what I showed there of decile 1 or 2 is still quite a lot of rain, but the vegetation is such that it really dries out so significantly that it is susceptible to fire, and that is a very real consideration. I don't think we can predict that when those situations will occur, but I think it's almost certain that you will have periods when the West Coast gets quite dry. In fact, you know, as we've seen this year, it's quite dry now, really, relatively speaking. Hopefully, we'll come back to more westerlies in the next month or so. It's beginning to look that way. But until that happens, it will be reasonably dry. As far as the global warming effect, I don't think I'm really the person to tell you that. I'm mainly concentrated on climate variability and synoptic climatology, and at this stage we can't discern that global warming signal in the weather systems as such. Some people claim they can, but I haven't been able to yet. But you can certainly see the warming signal, but it's a question of whether that changes the amount of moisture actually going into these systems. And as you saw from that diagram I showed, they actually forage a long way afield to gather some of that moisture, these systems, and they're already getting it from well to the north of our location. So that gives you an indication, perhaps, if the local temperature were to increase significantly, that you might see more input to these systems. But there's so many other factors come into it, mainly not just the actual temperature, but the temperature gradients that determine how systems form.
Mike, you talked about the seasonal fluctuations in sea ice in Antarctica, yes. And we often hear quite a lot about that in the media as well. So have there been changes over the recent years of the extent of that larger sea ice, or is that still staying pretty constant to what we would normally expect?
I'm not right up to date on it, but about 10 years ago it was actually increasing, but since then it's decreased somewhat again. But I mean, it's still a major feature of the circulation during the year. One aspect of it that perhaps we're looking more closely at is the thickness. The thickness of the ice is very important, and in some places that has decreased, I believe. But I haven't worked in Antarctic meteorology for quite a long time now, since 2002 or something. Thank you very much.